I have your attention, please? Thank you.
Yes.
So, probably most of you know me already. We've been course mate for 4 years now, so no need to introduce. We did a series of events in the past few weeks, so the department decided that this week I should give a talk for the final year project. So I will tell you more about those events later, but they asked me to somehow inspire the undergraduates to do research and to get published in journals. So that would be a waste of time if I do not give you a reason. Why do you have to publish? Why do you have to do research in the first place? Because I know most of you are not here for the science, but rather you're here just to get a degree and get a job afterwards. But just to get your attention, let me tell you that we have a program here in the university. It's called High Impact Research. You graduate right now from, okay, you don't need this, probably. You graduate right now from the department. You go out there, the job you get is 2,000, 3,000 ringgit. The job they give you here is 5,000 ringgit to start with. If you're so good, you can get 10,000 ringgit a month. And again, if you're so good, they will give you your own lab. You can buy your own equipment. 5 million ringgits to start with. You can hire your own people. So that's one reason, but that's not the main reason. Let's just go through some of the reasons I want to talk about. So when we are born, all humans, we are born as explorers. When your mother tells you that do not touch the pan, it's hot, you don't understand what hot means, so you go anyway and touch the pan, and from that moment on, you will understand what's the meaning of hot. And that's how you explore. That's how you are a researcher in nature. So then we go to the primary school. In primary school, they tell us 2 plus 2 is 4, and that's a fundamental fact that you have to use in your life in the years to come to communicate with other people. For most of the people who do math and philosophy, they know we have more than one numerical system. It doesn't make any sense to say 2 plus 2 is 4. But this is one of the easiest ones, based on 10. We have the binary, which is based on 2, then we have based on 9, based on 8. So it's not a simple fact, but in the primary school, they satisfy us that, okay, this is the simplest way, just stick with it. Don't ask questions. That's good, because say if as an infant, you were going to come up with your own language, then we'll have problems in communication with each other. So we have some conventions that we learn in the primary school. Like during the kindergarten, you mix the yellow and blue bucket of color with green. That's fine, because you're exploring new ways. So in general, you will learn x plus y is z, and you shouldn't ask any questions about that. Then you come to the university, supposedly that should change. Because university is not the place that you should memorize stuff and just head for the A plus or the 4.0 CGPA. That's not the point of the university. University is where we come, gather to solve problems. That's why it's called higher education. That's more than education. You are now, say, memorizing what Newton and Einstein and whatever has done. Well, Newton and Einstein, they were people like you. They came up with the idea, and that's expected from you to also learn something and at the same time come up with some new ideas. During our classes, well, we shared the same courses. I can say the thermodynamics, we had the heat gradient concept and all, and then we went to vector analysis, surface integrals, and dynamics, kinematics of particles. But nowadays, like, these were all mostly for the first few years. How much of these you really use in your project? Not so much, not so much. Because the educational system, not here in UM, anywhere else in the world, is that they throw different concepts at your face and they don't care, are you interested or not? So in research, you have freedom to choose where you want to go. Let me give you another reason for doing research. So we have many different problems that you might say as a manufacturing student, you should not be concerned about them, but I'll tell you how you can solve them. By 2050, the population of our planet will be about 9 billions. And by that moment, we will not have enough food. I'm not talking about Africa. Yes, Somalia, they have famine every year, and nobody cares, because it's only their country, not the whole world. But by 2050, because we're living in a global village, most of the food you consume doesn't come from Malaysia. Most of it comes from, say, China, India, and all that, which they have this booming population, and by 2050, they will have enough population to feed that they cannot export their food. So 2050, there will be a food crisis. As a manufacturing student, it's a very broad field. You can help solve these problems by addressing the issues with transportation. One problem is that if you grow fruits, you cannot easily transport them to the other countries. That would be one problem to solve. And manufacturing is everywhere. If you're looking at the transportation system itself, the packaging, coming up with new ways of watering the plants and everything. Then we have 2060, merely a decade after that, we'll have an energy crisis. We will run out of oil. And by we, I don't mean just Malaysia, not the United States, the whole world. Saudi Arabia will not have oil by 2060. That's based on the current pace of consumption. And oil is in our food, our clothing, and polymers, and the plastic bag they use, drugs, medicine, and everything. And above all, we have the fuel. We use gasoline for our cars and also for the electricity. More than 90% of the electricity in the world comes from fossil fuels, coal, gas, and oil. And we have got only less than 50 years to solve all those problems. And we are not anywhere close to that. So, okay, many people will say that somebody has found a solution for other diseases that we had in the past. Somebody came up with the idea of a smartphone. Now we have computers, we have quantum mechanics and all smart. We have supercomputers also. So eventually, for these problems, there will be people who will come up with the idea. But no, this is the time, because as we go into the future, there will be more and more problems. As I said, by 2050, there will not be enough food. Now at least we have enough food, so you can concentrate on solving the other problems. We have even bigger problems, which you might say that that's a long time from now. In 5 billion years, our sun, it will expand into a red giant, as we call it, and it will be 200 times bigger than what it is right now. So you open up the door, the sun will be covering all the sky with red, glowing, all the radiation coming through, all the heat. You cannot live. You have to go underground. So by now, we still have failed to send only one person to Mars, which is quite farther from Earth, from the sun. Imagine by 2050 we have 9 billion. By 5 billion years from now, we'll have trillions and trillions of people. How can we transport them to Mars? And one of the problems is the problem of manufacturing. It's too expensive to manufacture spacecraft. Come up with a way to solve that problem. Again, more fundamental problems. In a few trillion years, that's a long time from now, but you compare that to the science that we do nowadays, you will see that we're not solving any of these problems. What we're learning in the schools is just consuming whatever that has been achieved before. We learn about the ordinary differential equations, so what? You're not using them anyway. I'm not saying you shouldn't learn. I say that apply them, and if you cannot apply them, go to something else that you can use in your works, because that would be just a waste of time. In a few billion years, you all have heard about the Big Bang. Big Bang that started from one point, the universe started expanding. And recently, just 2011, we found out that the space itself is expanding, not the stars. So our body is 99% empty space, the nucleus and the electrons. And imagine that space in between the electrons and the nucleus, it starts to expand, will be ripped apart from our body. And you might say, okay, that's a few trillion years from now, there will be a solution. No, we're not anywhere close to that solution. We cannot even get out into Mars. How can we escape from this universe to another universe? And let me tell you, you put a hot cup of coffee in this room, which is quite cold, it gets cold after some time. This is because of entropy, right? From your thermodynamics, if you still remember. Well, I don't know, because our teacher said, I do not understand myself what's the meaning of entropy, and I found it out on my own. But the meaning of entropy is that you put a cup of coffee which is hot in a cold room. It wants to be uniform, so the heat comes out, it gets uniform, it's uniformly distributed throughout the room until there's no transition of energy between the coffee and the room. Same thing happens in our body. The chemical reaction, the food that we eat, which is turned into energy, is all based on a chemical reaction which has a certain enthalpy. And enthalpy is actually just because of entropy. If we run out of entropy, then no more. Nothing will move. The electrons are around the nucleus of atom, they will not move. The blood in your vessels, they will not move. Nothing will move. The life will cease to exist. So there are so many problems. I picked one of them about 2 years ago. The problem was that by 2020, computers cannot get any faster. The manufacturing techniques we use, they will reach a certain limit. You go read on the Intel CPU, it says 24 nanometer technology. That will stop by 2020. Because how small can you get? 10 nanometer, then what? And you might say, okay, by 2020 probably the computers will be fast enough that you will not need to have faster computers. That's wrong, because just 13 years ago, in 2000, we had computers, personal computers, and we were happy that, well, the computers they do not now occupy a whole room. We can hold it in our hand. And from 2000, we have moved to a place that a smartphone is actually a lot more powerful than the supercomputers that we had back in 2000. And computers are now everywhere, in the medical equipment, which are used to detect cancer, in your cars as in the form of sensors, and smartphones, definitely, computers, projectors, anywhere. The houses are becoming intelligent. The walls will change color and all that. By 2020, that will happen. And let's imagine that we cannot improve computers. They will not be smarter, they will not be faster, they will not be more energy efficient. So we will lose one part of the industry. What they do not teach you here at UM as a manufacturing student is that you all learn about classical manufacturing, machining, designing stuff and all. Well, you should know that 70% of the profit, not in terms of volume, 70% of the profit comes from semiconductor industry, not from classical mechanics and all. That is also manufacturing. If I take that computer or that smartphone, as a manufacturing student, I ask you, what part of this can you manufacture? Probably only the body, because you don't know how to produce the glass, not the LCD, not the microchip, not the antenna, not anything, not the camera, none of those. Which is sad, because that's manufacturing, semiconductor manufacturing. And so what I have done is quite, I would say, extraordinary, for reasons I will tell you. So we have publications. When you do a great work, you need to publish your work. And the more prestigious journals are, it's more difficult to get into one of them. At UM, we never, as far as I know, in the past few years, we never had an author as the first author of a work in a journal such as Nature. Nature publishes a series of different journals. The flagship is Nature itself, which has been published from the 19th century. And it's very famous and reputable in the academy. So nobody could do that. Well, I mean, you're talking about professors who have a team of postdocs, 8, 7, 9, 10 people, and they have millions of dollars of grants, and they've been working in this field for years and decades. Because when I talk about undergraduate research, most of people would say, we do not have enough knowledge, we do not have access to equipment, we do not have the money, we're not as big of a guy as their professors. But I will tell you that's just an excuse. It's not a reason for you to stop. So I took on a very great challenge. I said, not only we will solve the problem of computers not getting faster by 2020, we'll make them cheaper, but let us go on and cure cancer. Let us go on and develop an infinite source of energy, because by 2050 we'll not have any more oil. So I designed my own experiment. Well, I went to my supervisor, and my supervisor said, you see, we do not have any grant for undergrads. We cannot give you the money. I wanted 5,000 ringgit to buy a chunk of steel to make the chamber that I needed to make some of the nanomaterials that I will show you later. So what I did, I went to the backyard of the workshop. There's a pile of scraps. I took the small pieces, put them together, and made a very sophisticated device. That's not me. That's not me. That's called the molecular beam epitaxy. That's a machine that they currently use to make those fast computers. The problem is that it's too slow. It's too slow, you cannot commercialize that idea. It's only good for research. You make only one transistor in a few hours. And let me tell you that the i7 CPU in your computers, that has about 2.6 billion transistors. And that's only one computer. How can you make a CPU in an economic sense with this machine? You cannot. So I made something even more advanced. That's it. Which doesn't look to be so advanced, but it does things which that machine you saw, it doesn't. So let me go a little bit closer. That's it. That's a whole experimental setup. I machined that thing with the help from the technicians. And all the pieces you see, the welding bits and pieces, none of those I couldn't buy because I didn't have any money. So I just went to the workshop, find the leftover of the people, put them together, voila, that's it. So this was so advanced that for the cap of the chamber, to cover the air hole on the top, I had used another piece of material which just machined from other people's work. And that's the whole experimental setup. Most of you who work in the field of materials, maybe coating and all that you do, you know that you have to characterize the sample as you make it, to control it, how it is grown, how it is made. Well, mostly in a machine we saw that had several probes. Those probes are very expensive, a few $1 million each, to detect the X-ray and all. So I came up with a new idea to have the characterization method to control what is happening inside that chamber, which is a very advanced technology. That's it. Yeah. It's a bottle of water. So I was holding the torch myself. I called my friend who happened to be here. I said, come and hold the bottle of water for me. And that bottle of water helped us monitor what was happening inside the chamber. The things that come out, they hit the water, they react, you will see something that tells you what's happening inside. So this project, when I started, it was a 3-year project. About 10 people from physics and chemistry and engineering are working on that. They had $300,000 spent in 3 years, and it failed. They couldn't get that. So we did it in 3 days, with no budget, just me, nobody else. So that's what's done. Let us zoom, see what all the colorful stuff are, and I will explain for you what are different applications, how we solve the problem of computers and then cure cancer and all. This is one of the structures. We use a scanning electron microscope to see this structure. I call it a nano stewie because that looks something like the Stewie Griffin from Family Guy. So one of the problems with computers is that it's two-dimensional. It's on a silicon wafer, the transistor is here, another transistor is here. So the electron has to move all the way from this transistor to that transistor, and it generates heat in the way, and it becomes slower, and it's become less efficient. So what the researchers are trying to do, they want to make three-dimensional computer, just like our brain. Our brain has these neurons. The neurons are connected together in the 3 dimension, so they're very close to each other, and they can communicate with each other very fast. They don't get hot. And imagine that how much energy we're spending on the computer. It just gets hot, and the energy just goes away. The battery, which is consumed, it mostly turns into heat. So what happens with these, with the current manufacturing techniques, you can only do two-dimensional. Because you have a silicon wafer, you coat it, you etch, you remove some of the part, coat again, etch, remove some of the part. That's not going to work. That will not be a 3D structure. So this is a 3D structure. A similar structure, another structure, one problem that we cannot go to Mars. Why do we not go to Mars as humans? Well, when we go beyond the magnetosphere of our planet, cosmic rays and all the radiation from the outer space, they can hit the astronaut and cause cancer. And many of the people who went to moon, it's actually they're on the low cycle of the sun. The sun was not emitting so much radiation. And even then, they absorbed so much dosage of radiation, which could have potentially developed cancer in their early ages. So what happens is that if you go to the doctor, the X-ray machine is covered by this bulky radiation shield, which shields the radiation. It has an expiry date. After some time, you throw it out. So this is only a few nanometers. And to get the scale is that a human hair, on average, it's 100 micrometer. 100 nanometer is 1,000 times smaller than that, and that's it. So what happens, the radiation goes inside the structure, it gets dispersed, and it gets dissipated as heat, and it melts the surface, it goes to the second round. So only a few nanometer, you can even wear it on your clothes. It doesn't have to be bulky that you wear. And maybe it will be possible to go to Mars one day. So this is what we call quantum wires. So these are all the structures you make using the same machine, using the same procedure in less than 10 seconds. Less than 10 seconds. It's very fast. And you get them in very large amounts. That's what has never been achieved before in commercial techniques. So we call them quantum wires, just a fancy name, where it's just wire, but very small, only 10 nanometer in diameter. And when the wire is that small, it has some quantum behavior, which they call conductive, ballistic conductance. So what happens is that electrons in a normal copper wire, they move continuously. In such a wire, they jump. That's why if you had this for your internet, for example, your internet would have been millions of times faster than what it is right now. And so far, they have confirmed this. I mean, on very small scale in the lab for 1 transistor and for 2, because you cannot easily produce this material, up to now. But soon you might be able to see it as a consumer product. These are called quantum dots. Again, quantum is just fancy name. It's just very small crystals, nanocrystals, about a few hundred nanometers to a few tens of nanometers. Depending on their size, they give different colors. So in LCD screens, you can use this one. The difference is that it's so much efficient. It doesn't need that much electricity. And most of the battery in your phone and your computer, it does go for the LCD. And this can solve that problem. Another problem that the same structure solves is the problem of cancer. Now, when you do chemotherapy, it's a non-targeted therapy. That means they release the chemicals, and they can hit the healthy cells as well as the cancerous cells. And that's why you lose your hair, you'll be weak, and not many people even make through the therapy. So this is called a targeted therapy. So what happens, the small quantum dots, inject them inside your blood, they will go, find the cancer cells, they stick only to the cancer cells, not the healthy cells. From outside the body, they use a source of infrared light. Nothing, there's no contact, it's just light. We emit it toward the body, and these small quantum dots, they start to shake furiously. When they shake, they remove the cancerous cell, leaving the healthy cells unharmed. Same thing can be used for cardiovascular diseases. When your blood vessels are blocked by the fat, we'll send these inside, a little bit of infrared, voila, solved. No more heart attack. So again, same procedure, less than 10 seconds, we call this carbon nanofibers. Carbon nanofibers are good to reinforce composites. Like ceramics are very brittle. You drop them, they break. How to solve that problem? We add some of this inside them. So far, it has not been very plausible because it's too expensive to make one of these. Now, that has changed. We can use this also as electrodes in a lithium-ion battery. So if for rechargeable battery you have these, they have a very large surface area. They absorb the lithium ions, and the capacity will go up, and it will be a lot faster to recharge it. You might say, well, my smartphone just works fine, whether it's 1 day or 1 week, doesn't really matter. But when you're talking about electric cars, we have about the Tesla Model S. That is one thing which is lacking is its battery. The battery cannot last that long, and it takes at least half an hour or 1 hour to recharge, depending on the charging stations. So imagine we had this, the problem with pollution solved. The problem with oil and the gasoline and stuff solved. So, what is very good to publish, I mean, you can publish any work. Whatever work you're doing for your thesis, that can be published. But the question is, in which journal? Good high journal, the prestigious one, they don't like the results. They lock in the methodology. If you have a crazy idea, even if it fails and doesn't work, but shows some great potential for other people to work on, it's fine, they will publish that. But if you publish a result and say, we have this procedure, now we optimized it and we have 200% efficiency, no, you cannot publish that in Nature because the methodology is already there, you're just improving that. And that cannot be counted as high impact work, at least with the style of Nature and Science in all those journals. So, yeah, I gave you the following as an addition that you can open up. Currently, we have a program since 2011. It's called HIR, High Impact Research. The government has chosen among all the universities in Malaysia. It has chosen to give it more than 500 million ringgit in only 5 years, from 2011 to 2015, to spend and become one of the top 100 universities in the world. So this is a national project. It's not about one university or another. People from other universities come all the time. They join the program. The problem is that we have, in the past few years, we had good number of postgraduates. Now, postgraduates and undergraduates are on the same level in our university. I'm not sure, probably about 11,000. But the undergraduates, mostly, they're the one with the more energetic nature. They come up with the crazy ideas, not the postgraduates. Postgraduates, they're pretty old, they're here for the money, and yeah, anyways. So they cannot risk it. They don't want to risk to test the crazy idea, ask for money. If it doesn't work, then so what? If I had the grant, if I had the money, if I had that KPI, I had to meet this milestone, probably I wouldn't have risked. because I have to answer to my supervisors. But this time I didn't have any money, so no one to answer to. I did whatever I wanted. I used whatever equipment was available, didn't ask anything from the supervisor, and came up with that crazy idea. So once you come up with that crazy idea, you get it published in journals like Nature. Not only they will give you 50,000 ringgit for one publication, only one paper, 50,000 ringgit, you can be potentially considered for a research fellow at HIR. You can get 10,000 ringgit a month. And again, if you keep publishing these high-value papers, they will give you your own lab. Imagine your name is on top of the lab. And you can hire people from all around the world. It doesn't matter from which country. You can go to the other countries if you like. You have to come back after some time. The equipment you can buy, 5 million. You can start with 5 million. And that's it. So much potential in doing research. That was a reason to give you to do research, because just to give you inspiration, I don't think that's going to work. You should have a reason. Why should you leave the easy way? Go for the hard way, because the moment you submit a paper to a journal, every time you open your email, you're waiting for a rejection letter. So that's not a nice feeling. Not many people are willing to take that. But if there are good reasons that I told you, well, first there is the money, but again, 2050, 2060, all the problems that we need to solve, and you cannot say somebody else will solve it. Supposedly, you as the students, you should solve it. And I hope that some of you at least will consider that maybe your project doesn't have the potential to be that great. Anyway, go on and publish, show yourself, show your ability, and then for your postgraduate, come up with that crazy idea. And with the HIR program and what they have seen, that okay, an undergraduate can do it, they're willing to help. So use this opportunity as best as you can. Thank you. Thank you so much.